Welcome to this explainer. Today we're jumping right in to decode the invisible language of atoms. Now, as you probably know, nuclear magnetic resonance, or NMR spectroscopy, is an absolute game changer for understanding molecular structure. But we're not just here to count hydrogens today. No, we're going way beyond that to look really closely at how these atoms actually talk to each other across space and through their bonds.
So think about this for a second. How do we map the precise 3D shape of a complex structure without ever actually seeing it? It's a microscopic mystery, right? We obviously can't just stick an organic molecule under a regular microscope and expect to see its three-dimensional geometry. Instead, we have to listen. We have to tune in to the literal whispers between its atoms, a super fascinating phenomenon we know as spin-spin coupling.
To really get this, we have to start down at the subatomic level, where hydrogen nuclei basically act like tiny little magnets. Remember, any atomic nucleus with an odd mass or odd atomic number has a quantized spin angular momentum. For our hydrogen proton, it has two allowed spin states. When we hit it with an external magnetic field, these tiny magnets either align perfectly with the field, that's our +1/2 spin state, which is stable and lower in energy, or they stubbornly oppose it, which is the -1/2 state, sitting at a higher energy level.
All right, so our roadmap for today looks like this. We'll start with the magnetic world, then look at how atoms communicate. After that, we'll dive into 1-bond direct connections, 2-bond geminal twins, and 3-bond vicinal neighbors. And finally, we'll decode 3D geometry with the Karplus relationship.
Let's kick things off with part 1, the magnetic world.
Before we can build up the whole molecule, we really need to understand how these atomic magnets behave and share info. The best way to visualize this atomic communication is through the Dirac vector model. It basically explains how spin information transfers via electrons. It isn't magic, even though it kind of feels like it. The electrons hanging out in the intervening bonds actually ferry that spin information from one nucleus to another, completely through direct interactions between the nuclear and electronic spins.
Which brings us nicely to part 2, how atoms communicate.
Let's look at the mechanics here. The main takeaway is that electrons pair up with the nuclei to transfer this information. Thanks to the Pauli principle, we know pairs of electrons in the same orbital have opposed spins. Because of that, the absolute lowest energy state happens when the electron and nuclear spins are paired up, or opposed to one another. This gives us a really elegant rule of thumb. If you have an odd number of intervening bonds, like 1-bond or 3-bond couplings, you typically end up with a positive coupling constant. But if you have an even number of bonds, say 2 or 4, you usually get a negative coupling constant. Why? Because that extra intervening atom forces a parallel nuclear alignment.
Moving right along to part 3, 1-bond direct connections.
Okay, let's look at our first degree of separation. In a direct 1-bond connection, the interaction is incredibly strong and positive. And as you can see from the math here, the magnitude is directly tied to the amount of S character in that bond. For example, the 1-bond coupling between a carbon-13 and a hydrogen atom is super predictable. Using this formula, an sp3 hybridized carbon, like you'd find in ethane, gives a coupling of about 125 Hz. But jump to an sp2 carbon in ethene, and it's 156 Hz. Go all the way to an sp carbon in ethine, and it shoots up to 249 Hz. The hybridization absolutely rules the roost for this direct interaction.
Now for part 4, 2-bond geminal twins.
So let's step exactly 1 bond further out and look at atoms sharing the exact same central carbon. It is brilliant how, for these 2-bond or geminal couplings, the structural angle between the atoms strictly dictates how strong their interaction is. Literally, as the HCH bond angle gets wider, the absolute value of the coupling constant drops. In a standard tetrahedral sp3 carbon with an angle around 109 degrees, your geminal coupling sits roughly between -12 to 18 Hz. But the moment you start straining that angle in a small ring or opening it up completely, that value shifts dramatically.
Next up, part 5, 3-bond vicinal neighbors.
Stepping out to 3 bonds is where this atomic whispering really turns us into 3D architects. What's fascinating here is seeing how the side-to-side overlap of orbitals transfers information, which depends entirely on the dihedral angle between them. See, because the central carbon-carbon sigma bond is almost perpendicular to the carbon-hydrogen bonds, the electrons can't really interact strongly through the main sigma system. Instead, they have to rely on this tiny bit of parallel orbital overlap between the adjacent CH bonds, and that overlap is completely governed by the dihedral angle, which we call alpha.
And finally, part 6, Karplus, decoding 3D geometry. This is the real climax of our explainer. The Karplus equation is what decodes all this 3D geometry. It mathematically links the exact magnitude of that coupling constant right back to the dihedral angle we just talked about. Martin Karplus came up with this beautiful formula that fits the experimental data perfectly, where A is usually 7, B is -1, and C is 5. It is literally a mathematical key. It takes a simple coupling constant that you measure in hertz and turns it into a precise physical angle in three-dimensional space.
So let's see how this builds our complete spatial blueprint. Orbital overlap proves that coupling isn't just arbitrary lines on a graph. It tells us exactly how these atoms are physically twisted in space based on where that overlap is strongest. At 0 degrees and 180 degrees, the bonds are perfectly parallel or antiparallel, meaning you get maximum overlap and the largest possible coupling constants. But right at 90 degrees, the orbitals are completely perpendicular. The overlap totally vanishes and the coupling drops to basically 0. This is exactly why in alkenes, for example, trans couplings at 180 degrees are pretty much always larger than cis couplings at 0 degrees.
Which brings us to the big picture. Coupling is, without a doubt, the ultimate blueprint of molecular reality. By zooming out from those tiny subatomic spins all the way to 3-bond geometries, we've seen exactly how scientists map the precise architecture of a world we can't even see with our own eyes. We rely on the Dirac model, 1-bond hybridization, geminal angles, and of course the Karplus equation, not just to figure out what's connected to what, but to map the exact 3-dimensional conformation of the whole molecule.
I want to leave you with this thought. If we can read the structural blueprint of literally any molecule just by tuning in and listening to its atomic whispers, what new medicines, what kind of advanced materials is this invisible language going to help us design next? The more accurately we decode these 3D blueprints in solution, the better we can engineer the future. Thanks so much for joining me for this explainer, and definitely keep exploring the invisible world around you.